The next interesting case of solving x prime equals ax is when we have complex eigenvalues for a. So again, we're going to assume that the system is homogeneous. It's not x prime equals ax plus b or anything. We're going to assume that a has all constant entries, and we're going to assume that a is non-defective. So that is, for every eigenvalue we find, we can find an eigenvector also. So if an eigenvalue comes up with multiplicity k, we can find k linearly independent eigenvectors. So if a plus bi is an eigenvalue of a, and u plus vi is a corresponding eigenvector, then two linearly independent solutions of x prime equals ax are e to the at cosine of bt u minus sine of bt v. So u is the real part of the eigenvector and v is the imaginary part of the eigenvector. And e to the at sine of bt u plus cosine of bt v. Now this formula is a little tricky in my opinion because so sine and cosine each get a chance to be with the real part of the eigenvector, and they each get a chance to be with the imaginary part of the eigenvector. But when sine is with the imaginary part of the eigenvector, it has a minus in front of it. Otherwise, we have plus, plus, plus everywhere. Now, a minus bi is necessarily going to be an eigenvalue too. And u minus vi will be an eigenvector too. But we can ignore these. Because we're going to pull the a out of the a plus bi eigenvalue. We're going to pull the b out of the a plus bi eigenvalue, and then the u and the v are already occurring in the u plus vi eigenvector. Alright, so let's do an example. Let's solve x prime equals ax, where a is the matrix 3, -2, 4, -1. So we'll find the eigenvalues first. Determinant of a minus lambda I equals 0. So determinant of 3 minus lambda here and -1 minus lambda here, -2, 4 equals 0, means that 3 minus lambda times -1 minus lambda minus -8 equals 0. So what do we have? Lambda squared minus 3 lambda plus lambda, so it's minus 2 lambda, minus 3 plus 8 equals 0. Lambda squared minus 2 lambda plus 5 equals 0. I can't see how to factor that, so let's use the quadratic formula. Lambda is going to be one of the numbers negative b plus or minus square root of b squared 4 minus 4ac minus 20 all over 2a, which is 2. So we have 1 plus or minus square root of negative 16 over 2, which is 1 positive 1 plus or minus square root of negative 16 is 4i. Pull out the 16 to make a 4. 4i over 2. So this is 1 plus or minus 2i. And we can really just use the 1 plus 2i. Alright, so let's look at the 1 plus 2i eigenspace. So we have 3 minus 1 plus 2i in the upper left, and then negative 1 minus 1 plus 2i. In the lower right, and then negative 2 and 4. So that times v1, v2 equals 0. So let's see, 3 minus 1 is 2 minus 2i, negative 2, 4. Negative 1 minus 1 is negative 2 minus 2i, 0, 0. Now, in a 2 by 2 system, with a matrix having determinant 0, the row space has to be one-dimensional. It can't be two-dimensional. So that means that we can throw away the second equation. I think I'm going to keep this formula here because we're going to use it soon. So we can discard the second equation. So we have just negative 2 minus 2i, negative 2, 0. And if we divide by 2, that's negative 1 minus I, negative 1. Oops. That's positive 2. 2 minus 2i, 1 minus I, negative 1, 0. So that says that 1 minus I v1 minus v2 equals 0, or 1 minus I v1 equals v2. So as a basis, so v2 is 1 minus I times whatever v1 is. So 1 minus I is a good basis. But to use the formula, I want to break that basis element into a real part and an imaginary part. So let's write this as 1, 1 plus I 0, negative 1. Alright, now we can use this as the real part and that is the imaginary part in the formula. Oh, and I erased half of the formula. Alright, well, this is the second half and I erased the first half. But the first half is the same with cosine going with the real part of the eigenvector and sine going with the imaginary part, and the sine is going to have a minus sign in front of it. Let me put that back. Cosine bt u minus sine bt v. Alright, now 1 plus 2i is the eigenvalue. So the solutions are anything we want e to the at. A is 1. And then 2 is going to go in the trig function parentheses. So e to the 1t sine of 2t, the real part, 1, 1, plus cosine of 2t, the imaginary part, 0, negative 1, plus anything we want, e to the t. Now cosine of 2t goes with the real part of the eigenvector, and minus sine of 2t goes with the imaginary part of the eigenvector. So I guess this is a natural way to write this, but we could, if we wanted to, combine it into one vector instead of having all these sums of vectors and products here. So in case we wanted to rewrite it, so let's see what's in the first component. We've got c1 e to the t sine of 2t, and then that's going to be 0 there. So c1 e to the t sine of 2t times 1 plus nothing else, and then c2 e to the t cosine of 2t plus nothing else because there's a 0 there. And then in the bottom component of the vector, we've got c1 e to the t sine 2t again. And now minus cosine 2t. And the c1 e to the t is multiplying all of that. So put this in parentheses. And then also on the bottom we've got c2 e to the t cosine 2t. Let me write this on the next line. This is all supposed to be part of the bottom component, plus c2 e to the t cosine 2t minus sine 2t times negative 1. So I can make that a plus sine 2t. So this is the top component, and then this whole sum here is the bottom component. In case you think it looks better this way than that way, or in case in the book or somewhere else you see the solution written that way. It's exactly the same as the solution written this way. The end.